So let's go ahead and work a problem here mathematically. This is not something you'll have to do much on the exams, but it's important to be able to see that it actually works. I've got an equilibrium constant value for ammonia being synthesized, which is 6.8 times 10 to the fifth at room temperature. So this is a reaction which is very much favored going to the right. And so my question is, what happens if I decide to increase the temperature to 400? So I'm going from 300 Kelvin to 400 Kelvin in a problem which is going to be exothermic. So let's see what's going on here. Because my value here is going to be giving off heat and I'm increasing the temperature, this reaction is going to be shifting to the left. That means I'm going to be making less ammonia and more hydrogen and nitrogen. And as a result, I would have to predict that the value for K is going to go down. Well, let's go ahead and look at it. So it turns out that delta H is, as I said, exothermic. It's minus 92 kilojoules per mole. You can get that value thermodynamically from the tables. And then now you can stick this into the Van 't Hoff factor. So there's your value of 92 kilojoules that you'd have to turn into 92,000 joules. And there I have my temperature going from 300 Kelvin to 400 Kelvin. And I want to know what's going to happen to K. K, the ratio of K2 over K1 is negative, which means that K2 is going to turn out, when I solve for it, to be 51. So K has gone way, way down from where I started, from about 6 times 10 to the fifth down to 51. This is actually a pretty significant situation here. What this is suggesting is that for this particular chemical reaction, as I increase the temperature, my reaction shifts to the left, and I am making less of my product. So let's take everything we've learned so far about chemical equilibria and about stress and apply it to this incredibly important chemical reaction here. This chemical reaction right here is the Haber process. It's a process which is a formation reaction, hydrogen gas and nitrogen gas making ammonia. But this isn't just any formation reaction. This isn't just any delta H of formation. This is the one that produces ammonia. Ammonia is fertilizer. Ammonia is the stuff that makes your plants grow. It's the stuff that makes cats and dogs and people grow when they eat the plants. We need ammonia. We need this reaction to go to the right. So in this Haber process that people have created and have worked on to optimize as best they possibly can to make as much ammonia as they possibly can in as little time as they can, what do you think they do? Well, thermodynamically, they say, I need to shift this reaction to the right. What will shift it to the right? Well, one of the things that will shift it to the right is by removing ammonia. Because if you remove ammonia, the reaction will have to shift to the right because of the concentration change. And at the same time, they keep adding hydrogen and nitrogen. So keep dumping hydrogen and nitrogen in, keep sucking out ammonia. Le Chatelier says that will drive the reaction to the right. What about pressure effects? I've got 4 moles of gas on the left. I've got 2 moles of gas on the right. Evidently, if I increase the pressure, that I squeeze down on this system here, this will also cause the reaction to shift to the right. And as a result, I will produce more and more ammonia. So far everything's working well. Work at high pressures, add hydrogen and nitrogen, remove ammonia. That's going to drive the reaction to the right. And now, to top it all off, let's cool the reaction down. That's what this is saying. Because this is an exothermic process, if I want the reaction to shift to the right, I have to run it cold. If I run it hot, the system says, wait, I'm going to fight this by going this way. That wouldn't do any good to run the reaction hot at high pressure while adding hydrogen and nitrogen and removing ammonia. It's much better if I run it cold. The only problem with running it cold is that reactions don't happen as fast when they're cold. Remember, thermodynamics tells you that ultimately a reaction will happen, but it doesn't tell you how long it's going to take. As we will learn when we get to kinetics, if you want a reaction to happen fast, you heat the system up because you move all the molecules around. There's just that more movement, there's more energy of moving in that direction. Unfortunately, heating up only makes the reaction go in the opposite direction. So you have this sort of countering of the kinetic effect, which would cause the reaction to go to the right, and the thermodynamic effect because of this exothermicity that causes it to go to the left. Is there a solution to this? There is. And the solution is to develop some strategy by which we would be able to make the reaction go faster at lower temperatures, because then we could work at lower temperatures that would favor driving the reaction to the right. And that's in fact what lots and lots of scientists do. Scientists all over the world work on catalysis, because catalysis is the process by which I'm able to make a reaction go very fast by changing its reaction mechanism so that I can run it at lower temperatures. That's the secret here then to making the Haber process work. You make the hydrogen and nitrogen increase, the ammonia decrease, you work at high pressure, you work at low temperature, but you add a catalyst to speed the reaction up. This is a nice example then of seeing how it is we tie together all these ideas we've learned about Le Chatelier and chemical equilibria and coupling it with just a taste of what's going to be coming when we explore kinetics in a couple of months.